Okay, fine. Then let's start. So in the last class, we are discussing about the response of a second order instrument. So we have seen that how a second order instrument transfer function can be written. And mostly here we assume that there is no zero in that uh, instrument. Only poles, two poles are present. Now you know what I mean by zero or poles. And we start deriving, and then we have seen that we have three gains, which is k static sensitivity, three parameters, omega n, which is undamped natural frequency, and zeta, which is damping ratio. And we have seen that how a physical system can be modeled, or when we model a physical system, second order is transfer function may come naturally, and which is a second order instrument. When we want to measure some measuring through such mechanism, then the input output response dynamically can be related with the help of second order differential equation. That's what we call it is a second order system. Now, if we proceed, so these slides maybe we discuss little bit. So what I mean to say, so suppose step response of a second order instrument. So first thing, like the first order instrument we did, we read about the some known inputs like step response, output for the step input. If you give, so from the output you can determine the input, that is our objective. And then we can read about the ramp response, we can read about the impulse response, and we can read about the frequency response. That is the strategy, the way we do. So now let's start with the step response of a second order instrument. So okay, fine. So let's start step response of a second order instrument. So for a step input of size QIS, that means that at t equals to 0, q0 will be equals to 0, and when t will go, and dq0 dt equals to 0. So we can solve this differential equation 3.200 with the help of in time domain as well as in the frequency domain. So if we solve this in the time domain, we need a time domain boundary function, boundary condition, which is given by 3.201. And if you see, there are four uh, set of things we can do. First thing is zeta can be greater than 1. Zeta, that is called the underdamped. Zeta can be equals to 1, which is called the critically damped. And zeta can be within 0 to 1, which is called the underdamped. And when zeta is greater than 1, that is overdamped. And zeta can be equals to 0, which is undamped. So in such situation, we will get the solution, and you see that we get the solution. First case is it is overdamped system, which zeta is greater than 1. Second case 3.203. This equation is actually critically damped when zeta equals to 1, and last equation is underdamped uh, when this zeta will be equals to in between 0 to 1. In all the cases, you see as t tends to infinity, the k0 by kqis will go to 1. So these two terms will die out, it will go to 1. These terms here will die out, it will go to 1. Here, these terms will die out because the amplitude will be dying out slowly, although there is a sinusoidal term, so it will go to 1. So if you see these three terms, more things you can realize that for the overtime system there is no oscillation. So gradually it will rise slowly, slowly, slowly as t goes to infinity. Q0 by QIS will go to 1, or it Q0 by QIS will be equals to K, or Q0 equals to K into QIS. So some multiplication multiplied by the steady state of the input, that will go as t tends to infinity. Now for critically damped system also it will go to 1, or k multiplied by input, and under damped system it will oscillate, and gradually oscillation will die down because the amplitude is going to die down, and it will settle to the value 1 or kqis. So now if we plot this is a very important plot. So if we plot, so it is a non-dimensional plot. So x-axis instead of t, we plot it omega n into t, and y-axis instead of q0, we plot it Q0 by KQIS, so that our gain is taken here. So final state it should reach at 1, not the KQIS. So now if we plot this, you see there are sets of curves and zeta is written in all the curves. So you will see that for different zeta we will get some different types of curves. So let us consider zeta equals to 0, which is called the undamped oscillation. So you will see that it is going high, and the second peak is also going as high as the first peak. So there is no way the oscillation will die down. So it will keep on oscillating, and it will be very difficult to measure because the pointer will keep on oscillating. This is a sort of undamped system. Now if we increase the damping little bit, so you see it is a 0.02, 0.4, 0.6, 0.81. So what I said, in between 1 to 0, so it is a underdamped system. So now if zeta equals to 0.2, you see that this curve rises and then it comes down and then it goes another peak. So you note that first peak, second peak is considerably less than first peak, so the oscillation is dying down. So as zeta in between 0 to 1, the oscillation will present, but it will gradually die down and will ultimately reach to steady state. Now you note it, when the zeta value is going to high, the oscillation is going to less, and peak overshoot, this is called the peak overshoot, where this first peak appears. The peak overshoot is gradually decreasing and the oscillation is less and it is settling down. Now you come to the point that when zeta equals to 1, which is called the critically damped system. So here you see, for a critically damped system, it never goes up more than 1. So always it is below 1, and slowly it increases and reaches the steady state. Now for overdamped system, which is zeta is greater than 1, here it is given 1.5. You see the curve never rises below 1, above 1, and also it always, zeta is always less than 1. Curve is always less than when zeta is equals to 1. So it is always below the critically damped response and gradually rises, and it takes lot of time to reach the steady state when your zeta is more than 1, and so its response is not fast. So this is the full picture. So when we design a system, it may becomes a second order system, and that measurement system, the damping may be different, damping may not present. This is not desirable condition because oscillation keep on. So we need to give some damping, and based on the damping with damping coefficient zeta, whether it is in between 0 to 1 or 1 or 1 more than 1, the response changes. So this is the thing about the second order system. So generally when we do or design the second order system, zeta equals to 0 we never prefer, so it is not desirable. Zeta is more than 1 is also not desirable. So zeta in between 0 to 1 is desirable. Also oscillation is there, but oscillation dies down and the steady state it reaches quickly. So whenever you see any second order system, mostly you will see most of the cases that it works under the condition of zeta in between 0 to 1, and in between zeta 0 to 1 there is also a specific zeta which is mostly preferred. The reason will come from the frequency response, and when we read frequency response you will see which zeta is most preferable. That you will see from the frequency response. So that time we will read. For the time being, you think that zeta more than 1 is not desirable, zeta equals to 0 is not desirable. Generally, the second order system works under time condition, and it is the most preference case of operation. Although oscillation is present, oscillation dies down quickly and it reaches the steady state. So this is the step response of a second order system. We'll go keep on going about the step response more. Before that, I want to see if you have any question. Okay, do you have any query which you want to ask? Okay, then let's start the class again. If you have any query, you can ask or you can write it on the chat box so that I can see and answer. You can definitely ask, and if you don't hear or network is working, definitely quickly you ask, raise your voice and tell that this is happening. Okay, now let's go to, so this one we understand. So now suppose we have two different instrument and we have two different response. So we need to characterize the response with several parameters so that we can particularly say that this response is having this parameter this, and another response is having this parameter this, and which one is preferable, so that we can tell. So to do that, we will now characterize this second order, the output of a second order system for a step input in with the different parameters. So example, you have seen that we have seen that spring mass balance is an example of second order instrument. In physics lab, you have seen the galvanometer is a good example of second order instrument. The deflection starts and then it oscillates, it gradually die down. And so there are many second order instruments. In fact, many instruments which are higher than second order usually assumed as a second order instrument, and we try to see how they work. So let's go further. So there are two things definitely you see. One is the steady state, another is the transient. So transient means before reaching the steady state or the fixed value of the output keep on changing in a different way, which is called the transient. And when the transient die down, that means that first changing with time dies down, it settles to some point or near to some point, and that we call the steady state. So first let's see that what are the different parameters we need to define for a transient response. So first thing is that delay parameter or delay time. So delay time is the TD. You see in the curve, it is given TD. So TD is defined as the time which is required to reach the half of the final value the very first time. So once it reaches the half of the final value means steady state value. So at what time it reaches the half of the steady state value, so that time we call as the delay time. So you have seen the delay time is defined in the curve. TD is written and zero point 0.5 it reaches. Now the rise time TR. So rise time we define differently many places. So rise time is the time that required the response to rise from 10 degree to 90 degree, or 10% to 90%, or 5% to 95%, or 0% to 100% of its final value. So it depends how you are defining. Here in the curve, in the plot, you see we define the time rise time TR as the time to reach from 0 to the first final value. You see the first value of the steady state. First value, I mean to say, you see that 1, it is reaching several times because it is oscillating. So first it reaches 1 from 0, that we can define as TR. Also, we define many times TR from rise from 10% to 90%, or 5% to 95%. Here we have seen the TR as it rises from 0% to 100% of its final value. For undamped second order system, here whatever we have taken, it is a underdamped. For underdamped second order system, the 0% to 100% rise time is normally used. So for underdamped second order system, the 0% to 100% rise time is normally used. For overdamped system, 10% to 90% rise time is commonly used, because for overdamped system it takes lot of time to reach the steady state. So if we take the value 0 to 100%, it will take a unrealistic long rise time. So that's what we generally define the time between 10% to 90% for overdamped system. But here it is underdamped system, so it is customary to define 0% to 100% time taken for an underdamped system. So you see the TR is defined here. So here it is the time taken for the underdamped system. Now it's time the TP. TP means the peak time. That means you see for a underdamped system. So for overdamped system or critically damped system, there is no peak time. For underdamped system, you know that oscillation it rise to a peak and gradually die down. So the time it will rise the first peak, you see this is the first peak. So the time at which it rises to the first peak is called the peak time and it is defined as Tp. Now you come to the set maximum peak overshoot MP. So MP is called the maximum peak overshoot. So for an underdamped system, you know that it first overshoot is the maximum, then the overshoot is gradually die down. So the first overshoot where it goes beyond 1 or beyond the steady state value, the value it goes that is called the maximum overshoot. Generally, maximum overshoot carries is less meaningful compared to the percentage of maximum overshoot because how much it is reaching overshooting compared to steady state value that is important. So we define the percentage of maximum overshoot which is the MP minus steady state value divided by the steady state value into 100, that is the percentage. Now you come another parameter which is TS. It is called the settling time. So it is defined as suppose a curve is rising and then gradually falling, then reaching the steady state. So before defining the TS, we need to define the band. So which band you are considering the TS. So the steady state value where it is reaching, you can define the TS with the 5% band or 2% band or even 10% band. So suppose we are trying to define TS with the 5% band, then at the steady state value where it will reach, you define the 5% up and down values and you will get a band. When the output reaches inside the band and never goes out of the band, this is very important. The output is going reaching here, see inside the band and never going out the band. So this will become the TS or settling time. So this is where you define next slides. It is written. So peak time, and now I'm trying to read. So the peak time is the time required for the response to reach the first peak of the overshoot. That's what I said, and I give the first peak. That is the important thing. Maximum overshoot MP is the maximum overshoot is the maximum peak value of the response curve measured from the unity. And if the final steady state value of the response differs from the unity, then it is common to use the maximum percentage overshoot instead of only maximum overshoot. So maximum percentage overshoot is defined as the first peak, that means the C is the output at TP peak time minus the steady state which is C infinity divided by the steady state which is C infinity into 100. This is called the maximum percent overshoot or maximum percentage of peak overshoot. The amount of the maximum overshoot directly indicates the relative stability of the system. Now settling time, that's what I define. I am reading again. The settling time is the time required for the response curve to reach and stay within a range about the final value of size specified by the absolute percentage constant, absolute percentage of the final value. That's usually defined as 2% or 5%. So thus the settling time is related to the largest time constant of the control system, and which percentage error criteria is used, that is also very important. So sometimes we use, if we want to use very tight criteria, we use 2%. If you want to use the loose criteria, we use 5%. This is very customary to use 2% or 5%. You can define your own criteria, 10% or something else, and define the settling time. So this is all about the different parameters we need to define for a second order system. So let's see if there are any query. Okay, there is no query. Fine. Then let's speak again. So these are the time generally defined for the measuring system, measurement system of second order. And when you get the two measuring system of a second order, you generally compare the different times. Suppose one measuring system you have the rise time is less and another measuring system rise time is large. So which one you will prefer? Definitely So the measurement rise time whose is less, that you will prefer because that will give a most faster response. Now suppose settling time, one system has settling time less, another is high. So definitely you will prefer the less settling time with the same criteria. And peak overshoot, which one is less, that one you will prefer. So that is the point you need to see before choosing an instrument. Now let us see how we can derive the expression of rise time or peak time or so. So rise time means we said that it will rise to the steady state value. Here we are assuming that the output is steady state value is 1. So the point where output CTR will be equals to 1, that will be the rise time. So we put CTR equals to 1. So 1 equals to 1 minus e to the power minus zeta omega in TR into cos omega d TR plus zeta by root over 1 minus zeta square sine omega d TR. So once we keep that one everything, we see that e to the power this is not equals to 0. So inside that will be equals to 0, 1, 1 will cancel out. And from there we see tan omega dtr will be equals to this. And we define sigma. Here you see sigma we defined as the zeta omega n. So once we define the sigma zeta omega n, this expression can be written as minus omega d by sigma. Now the rise time can be defined as 1 by omega d tan inverse omega d by sigma with the minus sign, or this can be defined as pi minus beta by omega d. Beta is this angle what point, and this is omega n over 1 minus beta square. This figure is important. So if we know the omega d, which is also omega n, that means no zeta omega n, so we can easily calculate the rise time. Now let's come the peak time. So peak time means where the first peak appears. That means it is the maximum value of the curve. So we need to determine the maximum. With this is becomes a maximization problem. So we can derive the curve. We know the expression of the output curve for underdamped system, and for such system we can take the derivative, first derivative dc by dt or d output by dt, and that derivative at t equals to tp will be 0 because at that point it reaches the maximum value, and that's what I did. So dc by dt, you see that we keep it here and we keep this equals to 0, and then this last expression goes to 0, and from there you can see that sine omega t will be 0. So omega t will be 0 pi this, and first peak will appear at pi. So tp will be pi by omega d, where omega d will be equals to omega n into root over 1 minus theta square. So peak time can easily be calculated if we know the system omega n, that means that the natural frequency of oscillation, and zeta, that means damping factor. We can easily calculate. Now let's come the maximum overshoot and settling time. So these two are required. So maximum overshoot is the overshoot where is the maximum overshoot where it reaches at the peak time. So the maximum overshoot is the value of the CT when it reaches the peak time, or TP, which is equals to pi by omega t. So we can write very simple, MP will be equals to C at TP minus 1. That will be the maximum overshoot. Percentage of maximum overshoot can also easily be calculated. Now settling time is the time where it is reaching the 2% band or 5% band. That's what I discussed. So from here you see that the from 2% criteria. So basically when you see the second order underdamped system response, you will see there is an envelope, okay, through which this is moving. So you need to see this envelope is 1 minus e to the power minus 1 plus e to the power minus zeta omega t by square root of 1 minus zeta square. So you see this envelope will reach at the pointer. So this will not go on this envelope. So whenever these two envelope will reach at the 2% criteria, that point will be the settling time. So this is very simple. So when we do that, we see that the expression is Ts with the 2% criteria is 4 by zeta omega n, and with the 5% criteria Ts will be equals to 3 by zeta omega n. So with the help of, if we know zeta and omega n, we can easily calculate the settling time with the 2% criteria or 5% criteria. Now whatever I discussed here till now, let's see if you have any query or anything you ask. Okay, no query, so I'm speaking alone. Okay, fine. So now if you see that the criteria, whatever I discussed that I tell you every time that if you know zeta, if you know omega n, you can determine all these parameters. Now for many cases, the instrument you build, you may not know the transfer function of the second order instrument properly, but from the output response you may see that it is behaving as a second order instrument, as there is an overshoot and then oscillation is gradually dying down, and it's coming to the steady state. So then the question is, if you don't know the transfer function of the instrument, how you can determine all these points? So it is very simple. Suppose you have a electrical system and the output is electrical, or maybe the output may be the mechanical also, or output may be the deflected position of the light, or many other things. Whatever may be, if you want to know these values of the TP, TS, TR, all those things, and you don't know the transfer function, then basically what you need to do, you need to capture the output of the instrument to a through a data acquisition system. Suppose you have the output of the instrument is the volt, and that output of the voltage should go to the computer, and where you can capture the voltage values with respect to the time. And so you have basically two columns. In first column, you have a timestamp 0 second, 0.001 second, 0.002 second, like that. And the second column, you have a voltage, and which could be starting from 0. So if you plot that, you get a second order response under damped system, and from the response, you can easily calculate and see where it is reaching the steady state, and where it is reaching the peak, and when it is reaching the steady state value, and also peak time, rise time, delay time, settling time, and steady state value. And if any steady state error, everything you will know. So you have to grab the system output with the help of data acquisition system. So if you can do that, even if you don't know the transfer function of the system, you can easily calculate those parameters. And many times this is used, and now the lab is closed, and in our lab, which is the control and instrumentation lab, there are experiments with the servo system and all. So there we used to do like this. We used to grab the data output. From there we used to plot it. We see that it is a second order system, and then we try to determine all the parameters of such system. So that is quite possible. Okay, and there are methods also. So if you cannot model with the help of physics, and you are seeing that it is a kind of output you are getting, and there are methods through which you can determine the transfer function of the instrument, that we will discuss after a few classes. So that is also possible. So many times, you whenever you have a uh, measurement system, you know the system, you can design, you can model with the help of physics. Sometimes it becomes very complicated and you don't know what is inside. That is very difficult to model with the help of physical laws. So then you can use the data driven system. You can give many output, you can see the many inputs, you can see the output, and from there you can determine the transfer function, how will come very soon. And from there you can calculate the all the time parameters. And also, even if you don't determine the transfer function, by capturing the output when you give a step input, and seeing this input output uh, data at different time stamp or different time, whatever you have captured, from there you can also calculate the peak time, rise time, settling time, all those things, and maximum peak overshoot. All those things are possible. So now let's proceed. Now let's see if you have any query. We'll proceed to further. So still you don't have any query, so then let's proceed further. So you see that the next slides contains two curves. So here you see that we have a zeta versus the settling time and how the settling time varies with the zeta left hand side curve you see. So the settling time is basically plotted on the y-axis and the zeta value is plotted on the x-axis and for a fixed value of omega n. So you see that as the zeta value is increasing, the settling time is kind of oscillation, as you can see. Sometimes it rising, sometimes falling, and then again rise, then fall, and then after zeta value 0.7, the settling time increases rapidly. So you see that 5% tolerance band, if you take, the settling time will be less, which is quite obvious because it is a big band and the output will go inside the band more earlier than the small band, which is 2% tolerance band. And you see that for 2% tolerance band you have the settling time more compared to the 5% band, and after kind of 0.7 or 0.75 the settling time will increase rapidly till 1. Now, if you see that the right hand curve, what is the maximum peak overshoot with the zeta, you will see that the peak overshoot for the zeta, if zeta is 0, there is no damping, so there is maximum peak overshoot, and if you consider it as a peak overshoot, it's a 100% peak overshoot because it will go, if it is, say, 1 is the steady state value and your response started rising from 0, it will go to 2 and then again it will go to so 0, then again 2, like this. So 100% peak overshoot, and then if you give some damping, let's say for example a damping is 0.5 or so, then you will see that peak overshoot decreases very rapidly, and for a damping of 0.5 it is kind of 15% peak overshoot, and then if it is a, you see, if it is a damping of zero point 0.1, then the maximum peak overshoot is 70%. So this is how with the zeta curve you see that peak overshoot is, if as the zeta is increasing, peak overshoot decreases rapidly, and for zeta which is near to 1, let's say 0.9 or so, so literally there is very small peak overshoot, and there is almost no peak overshoot, and when it is 1 and beyond 1, there is no question of peak overshoot because the output response will not go beyond the steady state, so the peak overshoot will be 0. So this is the curve it says so. Now we'll come to one numerical examples. Before that I want to see, so this is all about the second order step response of a second order system and the different parameters, and many times you will face such examples because you have a second order instrument, many times you have, and you give suddenly the measurement value from 0 to some values, and whatever the output you will get, that is you need to see. So let's see if you have any query till this point. Okay, so all of these things you are hearing, right, and understanding, because it is a kind of one-way transmission, so I don't get any feedback or anything. So I'm sometimes very skeptical whether I'm speaking blindly or so, because you people never respond. Anyway, let's see. Go to the next slides. So there is one example, numerical example. It's very simple actually. So we consider a second order system and we think that we know that the zeta is zero point 0.6 and omega n is 5 radian per second. And then what will be the rise time, what will be the peak time, what will be the maximum overshoot, what is the settling time, all those things we need to calculate. So when we see that zeta is zero point 0.6 and omega n is 5, then the omega d, which is the damped oscillation, Omega n is the natural frequency of oscillation. Omega d is the damped oscillation, which is omega n into square root of 1 minus zeta square. So if we substitute omega n is 5 root over 1 minus zeta square, that means 1 minus 0.6 square, it will come 4. And you know sigma will be equals to zeta omega n, and it will be 5 into 0.6, it will be 3. So now if you take the help of the formula, so rise time will be TR will be equals to pi minus beta by omega d. We know that the beta is tan inverse 1 omega d by sigma. But tan inverse 1 omega d we have seen 4, sigma is 3, so beta is 0.93 radian. So pi is 3.14 minus 0.93 divided by 4, which is omega d, and you will see that TR is 0.55 second. Now you see the peak time. The peak time is Tp is pi by omega d. Pi value is 3.14 and omega d will be equals to 4. We have seen. So if you divide it 3.14 by 4, it will come 0.785 second. So now then maximum peak overshoot will be the maximum overshoot value. So MP will be equals 3 to the power minus sigma by omega t to pi, and if you substitute all the things, you will get 9.5%. It is obvious. Zero point 0.6 zeta is 0.6. So for zeta 0.6, you see here it is a less than 10%. So 9 point something. It is fine. From this curve also we can see it. Now settling time using 2% criteria, we have seen settling time values will be 4 by sigma. We know sigma value is zeta omega n, which is 3 here, so 4 by 3. So settling time is 1.33 second, and for 5% criteria, it is 3 by 3 will be equals to 1 second. So you see in this particular problem, so where TR will be equals to rise time will be equals to 0.55 second, and then peak time after sometimes it reaches peak, it is 0.78 second. Then after sometimes it reaches the maximum overshoot, and so it reaches the peak time, and then it reaches to the settling time, which is kind of 1.33 second or 1 second. So that is the way it proceeds. So in this problem we know all the values of the second order system, and the reversely, if we don't know the value, we can capture the curve, and from the curve we can plot the curve, and from that we can know the rise time, peak time, all those things. And that is one of the lab experiments, but you cannot do it because of this institute is now closed. So this is all about the step response of a second order system, and which is obviously very important. Okay, so everything is very clear to all of you. So we'll start talking again. Before that, just I want to know if you know when your mid-sem exam will be. What is the date? I don't see did not see the academic calendar. If you can write when your mid-sem exam is going to happen. If anybody know, okay, 20 to 26 September. Okay, so we have kind of 3 weeks more, right? So 9 plus. Okay, it's fine. So today we have uh, today we are completing 13 number of classes. So 20 it will be okay. It is fine. So do you want to give a quiz before mid sem? Yes, Saurabhena is speaking something. Please. I actually speaker was somehow switched off, so I could not hear. Okay, so I'll try to see that one exam and then meet same how we'll take. We need to plan for exam definitely. Okay, so all of you read the Doeblin mostly. I'm teaching from the Doeblin. All of you read the Doeblin. You read the Doeblin and solve the problems. Okay, fine. So let's start again. So repeatedly, I'm saying you read the Doeblin because Doeblin book is available online, and you can see my Doeblin books here. This is my Doeblin books, and according to Doeblin books, we are at the page of 157, and we will gradually moving. So you read Doeblin books, okay, and we are in a chapter which is named there as a generalized performance characteristics of instrument. Okay, so all of you read Doeblin's. Doeblin is a nice book, and this chapter we are taking from Doeblin. Okay, so now let's proceed. Okay, so now the next what we read, that is a terminated ramp response. What is the meaning of terminated ramp response? Let us try to understand. What is the meaning of terminated ramp response? So, okay. So till now there is no query, right? So I'm moving further. So if you ask anything, I did not respond. That means my speaker was switched off. You can ask it again. There is no issue. Actually, my speaker was switched off. That is what I may not hear you. So if you want, you could speak again. There is absolutely no issue. Okay. Now let's start. So another thing is that terminated ramp response. This is actually very important because whenever you say that there is a step response, we always assume that at the point t equals to 0 minus, it is 0, and at the point t equals to 0 plus, it is 1 or some value. That means from the 0 it gradually rises to some value and stay there. So this is kind of very absurd because suddenly nothing can rise. So whenever any signal rises or you give, there is maybe some time, it may be very less, or maybe some time is required to gradually go up. For example, if you are touching, you have a temperature and you are touching the bulb with that temperature. So it may look like step, but you see that gradually, that if you see the microscopically, gradually the bulb is coming and dipping into it. So gradually it's going to get the response. And many other places also, and many places you can assume it is a kind of step response. Many other places you cannot assume that absolute step response. It is a kind of terminated ramp response. If you see the figure here, the terminated ramp response is a kind of a curve which is rising slowly, which is rising from 0, and then it is terminated to the value of 1. That means at 1 it reaches the steady state value and it never rises. So this is called the terminated step response. And for a second order system, if you see here, we can write, so there are two parts basically. So we can write the equation as the d square by omega n square plus 2 zeta omega d by omega n plus 1. D is the derivative. You can write s there into q0, which is the output, will be equals to kqi, which is the input. Now qi is very interesting. Up to the time capital T, if the time is in between 0 to capital T, the input is small t by capital T. That means it is a ramp input. It is increasing with time. Now, whenever it reaches t, the qi becomes 1. So, when the time is in between 0 to t, capital T to infinity, the qi is 1. So, that is the point. So this can be solved in the two conditions. So we solve this. If you solve this, you will get the solution. The first condition, first part of the solution is be in between. It is 0 to capital T. So this is going to be 0 to capital T. So you see, this is a q0 by k will be equals to small t by capital T minus 2 zeta by omega n t plus 1 by omega n t square root of 1 minus zeta square e to the power zeta omega n t sine square root of this plus phi, where phi is equals to 2 tan inverse root over 1 minus zeta square by zeta. So that is the phi. So now if you see that the equation 3.208, that is the output for the input, which is ramp. So it is in between time 0 to capital T. Now if you see the equation 3.209, this expression is the output for the time which is greater than t, capital T, and up to infinity. So this is a quite long expression. If you see that this expression is quite long, and so if we combine these two, we'll get the complete output response. First part is for in between 0 to capital T. The next part is in between 0 to capital T to infinity. Now if we plot these two expressions, so there is some point we should discuss. If you see the equation 3.208, okay, so immediately you will see this equation is for 0 to capital T, and there are 2 points we could say. There is steady state error. So in this point, if you see this expression, there is a steady state error. You see that small t by capital T, the first term is the input and this is the output. So for infinite time, if it is capital T is infinite, so this right and last term will die down and first term is the input. So the error will be 2 zeta by omega n t. That is what it is written. There is a steady state error of 2 zeta by omega n t. Now the transient error can be of no larger than 1 by omega n t into root over 1 minus zeta square. Now, if zeta, there is no damping. If the damping is less or no damping, the steady state error is 0. This is very, very important statement. You all should remember. So, for a no damping system, a ramp input, the steady state error is 0. The transient error is a sustained sine wave of amplitude 1 by omega n t. Therefore, if omega n is sufficiently large respect to 1 by capital T, the transient error can be made very small. Even the damping is practically 0. This is very important observation, and this type of treatment can be used when a system of second order we develop but we have very less or negligible damping. So what I am saying, let me state again. So if zeta equals to 0, the steady state error is 0 and the transient error is a sustained sine wave of amplitude 1 by omega Tn. Now, if omega Tn is sufficiently large relative to 1 by T, so then transient error can be made very, very small even if the damping is practically non-existent. This result, if we see the earlier equations, these results are based on that. This is a very, very important statement. That's what I copied it. Okay. So this result is based on equation 3.208. That means in between 0 to capital T. But this is also true for the next expression 3.209. This one, when in between T to infinity. This one T to infinity. And since the transient induces at t equals to 0 by the increasing ramp is essentially the same as the induced t equals to t by a decreasing ramp. So the point what I'm trying to mention, if there is a system whose zeta is very less and almost 0, and you give the terminated ramp response, and you make that the omega n is sufficiently large compared to 1 by t, sufficiently large compared to 1 by t, then the transient error can be made very small with such system. So that is the important thing. So if we see this one, you see the left hand side, figure, which is a kind of step response of very small amount of, very less amount of zeta. You see that if you give the step response, this will go high, and then next peak is very less compared to this, because zeta is very less, negligibly small. So it will keep on going like that. So step response is like that. But here if you see the ramp response, terminated ramp response for such system, it is quite similar to that of the input. You see q0 by k is there, time is there. So it is kind of similar. Okay. And here in this case, if you see that q0 by k is there, it is very small time, like this peak. This one is zoomed here. If you see, little bit go down, then little bit up. So it is almost following the ramp, terminated ramp, with some small amount of error, very small amount of error, you see. And then when it reaches the steady state, that step, it also follows the step for a small amount of error. So what is the conclusion? This is very important conclusion. I think this is the last slide. So this is very important conclusion. The conclusion is that if we use a system which has the very very less damping coefficient zeta, so in such a cases, if you give a terminated step instead of perfect step, if you give a terminated step, if you give perfect state, what will happen? It will just oscillate. Okay, but if you give a terminated ramp, that ramp and then state, what will happen? It will easily follow the input of the terminated ramp. That means when the ramp is there, it will like ramp with small error oscillating up and down. When the step comes, steady state come, it also follows the steady state with very small amount of oscillation, and that can be made even small if omega n is much larger. So this is what I mean to say. So I don't know whether you understand or not. You can ask, even if you don't understand, you can ask me that, sir, please repeat. That is also very obvious. I will repeat it, but you are not responding at all to anything. Okay. So hope you understood. Even if you write that you understand, that is also kind of encouraging to me. I do request to you, but you never uh, see do this. Anyway, it is up to you. So now we said that I have two classes. So now I will take some rest, maybe 5-6 minutes, and after 5-6 minutes again we'll start. So for the time being, we can dismiss the recording and stop sharing, and maybe we may be online or so, and maybe after uh, 5-6 minutes I'll join and then take another class. Okay. So I'm speaking continuously.